This morning I will speak about applications and consequences of this result that we saw yesterday. So I will just recall the result. So we start with SM eta, a graded surface, and so we have constructed a triangulated category, and this is constructed via this very technical A infinity technique. So as H0 of the twisted of some A infinity category where S is a full, is any, in fact, full system of graded arcs. And what we have seen also is that if D is a dissection, so remember that a dissection is almost a full system of graded arcs, but so in each polygon so it's like you take a minimal full system of graded arc and then you remove one arc corresponding to the boundary, so that you have such picture. So the surface is cut into pieces like this. So then we also have an equivalence. So in the Fukaya category of S is equivalent to H0 of twist AD. But in this case, AD is really equivalent to, so it's a category. It's a because we have mu1 which is 0 and mu greater than 3 which is 0, so it's really a category, and it's given by a quiver. So it's equivalent to the projective module over some quiver modulo some relations, and this quiver is really given like this. So I put one vertex for each arc of my dissection. I put arrows like this, and and here I have some zero relations. So it means that the composition of these two is these two arrows is 0. The composition of these two arrows is 0. And these arrows, they may have some degree. They will have some degree, but so so this is a graded quiver. Okay, and in that case, so it's somehow this category is much less scary than the very abstract construction, because it's just the bounded homotopy category of this category approach KQ over I. And so today, well, in the first part of my talk, I would like to explain how we could use. So we have somehow a geometric side, which is maybe this one. And here it's a very algebraic construction. It's just given by an algebra. You take the derived category of module over this algebra, or the bounded homotopy category of this algebra, and here we have lots of tools coming from representation theory to understand this category.
So why didn't you start just by defining this category by considering only sections?
Yes, we could have done that, of course, but so one point would be, okay, I could have just define this category AD without speaking about A infinity structures. But then it's not so easy to prove that if I take two dissections of the same surface, I have the same category. I get the same category, and really because in the proof of Hayden-Katsarkov-Kontsevich, what they do, if you start with two dissections, you have to complete them, and to complete them, then you end up in the A infinity setup, and then you flip or something like this. So you really need this A infinity, but yeah. So the first result is something that I already mentioned yesterday, but so I would be a bit vague in the statement, but so it's due to HKK again, and also by a work by Oper, Plamondon, Schroll in 2018. So yeah, I think I should cite both and say that the indecomposable objects of Fouque S are in, so here I should say canonical bijection. And here the word canonical, it really refers to HKK. It's because of their canonical equivalence. So first, homotopy classes of crowded arcs up to orientation. But yeah, as you see, I mean, I was considering arcs up to orientation anyway. And homotopy classes of graded closed curves together with some parameter lambda in my field. So here, remember, we have seen yesterday that somehow in the cylinder case, when the line field is such that this curve can be graded, then we have this we can build some kind of twisted complexes like this, twisted complex like this. So maybe just to mention, so what Oper, Plamondon, and Schroll did was they sort of, so as I said yesterday, this algebra, they are somehow well known in representation theory, so there were already plenty of results about them. And what they did is they translated these results, these known results, in terms of the surface, which was quite a huge work, but they used some known result about this category, which was described in a very combinatorial way. And Hayden-Katsarkov-Kontsevich, in their paper, they also used this side at this step, and they also use some representation theory techniques to show that you have this object and you don't have any more object, which is somehow here you can guess more or less how we can associate to, if you take a graded arc, how you could build a complex from this graded arc. But then one thing is to check that you have no more object than these two objects. So it just, yeah. Okay. So now I would like to state another theorem here about this category. And here again, I should mention HKK again and a joint work with Plamondon and Schroll and there is also a work by Hopper in 21, which is related to that. And what we can show is the following, that if you take two graded surfaces, so you may ask when the corresponding categories are equivalent or not. And the answer is as follows. So there is an equivalence between these two categories if and only if there exists a diffeomorphism from S1 to S2, so preserving the orientation. So, preserving orientation. And with preserving also the mark points and preserving the line field, but in a sort of weak way, because if I pull back the line field of eta 2 using this phi, so I get a line field on S1, and I want S1 to be homotopic, eta 1 to be homotopic to this, the pullback of eta 2. Okay, so this direction of this theorem, so it's not very surprising, maybe, this theorem, because at least, yeah, well, you should expect something like this, of course. So this direction is really almost by construction of the Fukaya category that it works. Because, so the only thing to check is that when you have two different line fields but homotopic, then you get some, you get some equivalence. But this is something quite easy to check, because you can start with a full system of arc, of graded arc, with respect to the first line field, and using the homotopy, you can sort of move the grading to get another. Yeah, I mean, this is almost by construction that it works. And so what we did in this paper, it's to prove the converse. And maybe I will say a few words about the proofs of this. So because to prove this, yeah. Yes, it's just an equivalent, a triangle. it's a triangle, an equivalence of triangulated categories.
Are you also assuming that, for example, the individual possible associated with some arc is sending to the individual possible associated to that same arc? Hypothesis?
No, we are not assuming this, but then no, we don't assume.
So just an abstract equivalence.
Just an abstract equivalence between triangulated categories. I mean, we want this functor to be a nice triangle functor, so it sends triangles to triangles. But that's all. But then, I mean, then because you have this, then using the so from this equivalence you get this phi, and from this phi you can send a curve to a curve, and yeah, then you should expect that it behaves well with this. But this will be a consequence, and yes. Yes, so yeah, this is also something I mentioned a bit yesterday. You have much more than this, in fact, but I just decided to skip this. But as I said yesterday, morphisms between two objects are given by intersections. So if you have a graded arc that intersects itself, then it means that you have some extension of the object, something like this. So yeah, but it's really like if you take two objects, a basis of the home space will be given by the intersection between these two objects. And yeah, and this is something also that Oper-Plamondon-Schroll proved. But yeah, you have much more than this. For instance, also in this category KB Proj, you have other structures. So, for instance, you have you can apply Auslander-Ruyten theory for in case you know the name. This is something very useful in representation theory, and we can understand almost split triangles in this context in terms of the surface. For instance, like lots of things that are known in representation theory, they could be translated in this in the topology side, and we could understand things. So the idea of how it works this way and in this direction, it really uses strongly representation theory, because like so step one would be first to find D1 and D2 dissections of S1 respectively S2. Such that the corresponding quivers, so Q1 and Q2, are of degree 0. So they should, you can find such dissection. So you just find some curves so that each of the arrows will have degree 0. And now the question is really, so then you get two algebras, lambda 1, lambda 2, and you start, so then you start with this equivalence and then you try to do something with this equivalence. And now we use a very useful theorem in representation theory, which is due to Ricard in the 90s, which says that if I have two algebras, so let A and B be finite dimensional algebras, then we have that KB proj A is equivalent to KB proj B if and only if there exists an object T in KB proj A with the following properties. So first, there is no extension between T of T with itself then secondly, the endomorphism algebra of T is isomorphic to B, and the third point is that somehow that T is sort of maximal in the category, that it generates a category KB proj, but then it's enough to assume that so what do I mean by this? So this is T is by definition would be the number of non-isomorphic direct summand of T. Okay, so we have this theorem that tells you that when you have two algebras, they are derived equivalent, so they have the same category like this, if and only if you have the existence of such an object. And maybe to come back to your question, Gregor, if you have such an object, it is somehow, you can build such an equivalence, but it may be not the equivalence you started with. So if you have some so from this you build an equivalence, but not all equivalences are given by this. It's just that, and how to build this object T, it's really here you have the object A, you send it to something, you have your object B, and T will be the object which is sent to B, and then it's completely clear that so the object B satisfies this property. So since it's an equivalence, the object T should satisfy the same properties. But yeah, it's not in general. This equivalence can be maybe more complicated. Okay, and so such objects are called tilting complexes, and this is a tilting complex T, and this is a very developed theory in representation theory. Okay. Yes, so maybe, so here maybe I should maybe give you an example of, so just start with A being the path algebra of this quiver. So then a typical example of such an object, well, maybe a very trivial example would be just you take T to be A itself, which which is the sum of P1 plus P2 plus P3. These three objects, projective objects, and this is, and then and T is just A itself. You come back to yourself, and of course you have an equivalence here. So it's like the trivial example, but just now I could give you a non-trivial example. Yes, you take home from T blanc, and in the other direction you take the tensor product by T, or the derived tensor product by T. So here it would be so T has a left B module structure, so you can do this like this, and here and it would be on T blanc, well, R on, and left tensor product. But yeah, not all equivalences are given like this. Just so now I could take A to be so I could take this object, so you can check, it's an exercise, you can check that T is actually satisfies this property. Well, the fact that T has 3 indecomposable summands, it's clear. So this one is okay, and you can check this one. And you can also try to understand the endomorphism algebra. So you have to understand the endomorphism algebra, you have to understand the morphism between these 3 indecomposable objects, and what you get will be you have a morphism from P2 to P3, and now you also have a morphism from sorry, what did it work? No. This is not okay. So then the endomorphism algebra is the path category of this quiver. So this is Ant. So then you get that this quiver is, well, derived equivalent to this quiver. Okay. And yes, and what we could prove, so then we proved that using this this description of indecomposable objects and of the morphism between indecomposable objects, we could prove that a tilting tilting objects complexes in this KB proj lambda 1 are in bijection with graded dissection on S1 with the property that so my dissection should, so when I say graded dissection, it means that yeah, no, it doesn't mean anything. It's the usual definition. When I have some marked a boundary, a marked segment, and I have two arcs of my dissection ending at this thing, I want this arrow to have degree 0. I want this index to be 0. So this is for any arc. Because really, this arrow, if it has a degree which is not 0, it will give me something non-trivial here with I corresponding to this index. And here I just want to have something non-zero when I is different from 0. So that's why I want all the arrows to be 0. And of course, to be sure that, so it's sort of, again, one direction is more or less clear that if you have a graded dissection with this property, it gives rise to a tilting object. It's almost by definition. But to check that, if you have a tilting complex, it has to be given by a graded dissection. You should know something about all the objects. So you should like exclude, for instance, a closed curve and so on. So yes. And now, from this theorem, now using this time using the topological side, we could prove the following. We could find a complete numerical derived invariance for general algebras of degree 0. And this uses strongly the work of Lekili Polichuk, from 2018 also, who so what they do is that they are also working with these Fukaya categories, and they study the action of the mapping class group of the surface on the homotopy classes of line fields. Or line field on S. And so you have, so this mapping class group acts naturally on the homotopy classes of line fields on the surface, and they describe the orbit of this. And they prove that the orbit of this are encoded by winding numbers of, like if you know the winding number of a basis of the fundamental group, typically you can build this numerical derived invariant. So this is really, yeah, you want to understand the orbits of this action. And you get, and so here maybe I could also, so now it's completely understood this, and it's even, yeah, there is this software used by people in representation theory, which is QPA on GAP. It's quiver and path algebras, and now so it has been done by my student. So this complete numerical derived invariant is now. You can check. I mean, if you have two gentle algebras, you can just enter them into the program, and it will tell you whether they are derived equivalent or not. So maybe just to give you examples, so where we yes, it's just a bunch of integers. So it's really something that you can compute using all winding. I mean, you take a basis of the fundamental group and you compute the winding numbers of this basis, and from this number you get the. I mean, you should know also the genus of the surface, this number, also the number of boundary components. This number, of course, they play a role, but this is clear from them. And yeah, so just example. So remember, so we had the disk. So the disk with 4 mark points. So I have like this dissection, which is possible. So here, for the line field, I don't have so many choices. I mean, all the line fields, they are homotopic in a disk, so there is no condition on the line field. So any dissection should give me a derived equivalence algebra. So I have also this one, and I have also maybe so here I get this algebra with a zero relation. Here I get this algebra with no zero relation. Okay, it's like this. And here I get this algebra. Okay, I have also the symmetric one to get the other one. Oh no, it's the same. Okay, so that's okay. I could also get this one, but that's all what I get. In this case, for 4 points, it's very easy. So all these algebras are derived equivalent. Now if I come back to the cylinder, so if I take the horizontal line field, so now I have some choice on the line field, and they maybe give me some different algebras. And I could have taken this dissection, and here I get this algebra, which has degree 0. So yeah, it's just this algebra, and it's not derived equivalent to this algebra. So remember, this was the other example of a dissection of this. So where here I would take this and this. And yes, this is, but this one, if you take the horizontal line field, then this algebra doesn't have degree 0. But it will have degree 0 if you take this line field doing like half term. So they are not derived equivalent because they correspond to different line fields. So this is more or less, yeah, this is a consequence of this theorem. Okay.
So they are. What is the role of the line field?
It's just that here the line field is really this one. And here, to get this algebra in degree 0, I need to take the line field doing some kind of half turn. And they are not homotopic because here the winding number with this line field of the generator of the pi 1 is 0, and here the generator of the pi 1 has winding number 1. So, okay.
Just look at the right example and I take the same line field as on the left example.
Yes.
I still get to be the.
Then yes, you still yes, but if you take this line field and this dissection, you get this algebra, but some of these arrows will have degree 1. And
Why do I like this?
it just so the question was more. So here I just built some. I mean, it gives me some. So it gives me some invariant for gentle algebra of degree 0. But this is true that okay, if this one is lambda 1. Say this one is lambda 2, it's a graded algebra. I call this one lambda 3. So it's the same algebra, but as a graded algebra is not the same. So it's true that I have lambda 1 is derived equivalent to lambda 2, but they are not derived equivalent to lambda 3. That's the statement. So just now I would like to yeah, in the last 15 minutes, I would like to to speak about a little bit about my last work with Pierre-Guy Plamondon. Just appeared on the archive 3 weeks ago. And so I won't have so much time to explain, but the idea is the following. So I start with SM eta, a graded surface. But now I added something. I added sigma, an automorphism of the surface of order 2, and I assume that the line field is sigma invariant. So now what I can do is that I can make the quotient of S by this automorphism sigma, and then yes, I'm sorry. I just realized that this is not completely correct what I wrote here. I will add. I need to add a bit of hypothesis. I was simplifying a little bit too much. So, yeah, which are given by degree 0 dissection. So this would be the yeah. This is something we have to. So somehow, like I assume the step 1 that I've been given some dissection of degree 1 so that I get quiver of degree 0.
So
Sorry.
you mean that they exist?
So I mean in my statement there exists T1 and T2.
Okay, so when
Yeah.
you say it's given, it's just it exists.
Yes, it exists. yeah, this is, yes, because I was just realizing, yeah, I tried to make the statement to fill into this talk, and so I mean, here, for instance, I could take a more complicated line field so that the winding number is 2, and if the winding number is 2, I guess I cannot find a dissection with this property. But like the aim was more, if I am given 2 general algebra of degree 0, I'm just wondering if they are derived equivalent or not, and this was the question. Yes, you can. Yes, yes.
With that condition, lambda 1 you are equivalent to lambda 2. That's not covered anymore by this theorem, right?
It's still correct, but this one is as a DG algebra. So this is true that they are derived equivalent. The derived category of this algebra is the same as the derived category of this DG algebra with this grading and 0 differential. And so this is still this is okay. This is just a consequence of HKK construction that these two are derived equivalent. But the fact that these two are not derived equivalent is somehow the converse direction. So you need to check that the line field, they are not homotopic. So the categories cannot be the same. And if you remember, so here somehow we have, like in the category corresponding to this line field, we have more objects because we have this object corresponding to this closed curve. So you have this family of 1 parameter family of indecomposable object, and here you don't have. So yeah, they cannot be derived equivalent. You have much more objects here than here. So yeah, I take a surface together with an automorphism of order 2, and I assume that it has some fixed point with finitely many fixed points. And the aim is to construct a Fukaya category, a Fukaya type category for the quotient of S by sigma, which has a structure of an orbifold. So because I have some fixed points, so just example, so I just start with a disk. I take again the horizontal line field, and I could take just the rotation of around the center. So now I have one fixed point, and here, so of course the line field will be invariant by this rotation, and so this would be S, and the corresponding orbifold will be again a disk, but with only 3 things. And here, so this is the orbifold point. And somehow, so here the line field is something like this. And here it will be more, I don't know, I have to fold it. So I'm not sure that I want to draw it, but okay. So this is, and yeah, this was our aim, and the reason is as follows. So what do we consider something like this? It just because it's a question appearing in representation theory. So here I could take a dissection which is invariant by G. So for instance, I could take this. So maybe I should so So I could take this dissection, and what do I get? So I get an algebra, which is given as follows. So it's just a path algebra of a quiver. Maybe I should write sigma of 1. Yeah, I will write prime, 2 prime, and 3. I get this quiver, and the action of sigma is just the symmetry. And now there is a natural construction that is considered in representation theory. This is a construction of skew group algebras. So this was introduced by Eden Heiten and Christine Rittmann in 1985. And so the construction is as follows. So if a group G acts as acts by automorphism on an algebra lambda, you can form the skew group algebra. So it's written like this. It's just you do the tensor product of this algebra by the group algebra of G. So as a vector space, it's just lambda tensor by so as vector space is just generated like this by lambda tensor kg. And the multiplication is given as follows. So if I take two tensors, the product of my two tensors will be just that I twist this lambda prime by the action of G, and I get a tensor again, which is this one. And so if I take lambda to be this algebra, and if I compute what is this algebra, so here, I mean, this you can consider this construction for any group, and but so yeah, so here G is yeah is Z2. And we want, I mean, yeah, just for this construction, you don't need any more hypotheses. But so here, what happens? Okay, you want to understand this algebra in terms of quiver. So you want to understand the projective object in this category. To understand the projective object of this category, you take, so it's like here, you take the unit of the algebra, and the unit of the algebra, so it's the isomorphism from lambda to itself, it splits into idempotent. So it's E1 plus E2 plus E3 plus E1 prime plus E2 prime. And each of these idempotent will give you a vertex in your quiver. Will give you an object. So EI lambda is a projective lambda module. Okay, so now I want to understand this. So it's the same, I do the same game. I take the unit of this algebra. So the unit of this algebra is 1 lambda tensor 1G. So yeah, maybe here G is it's better instead of writing in Z2, I prefer to write in the group generated by sigma. So it is, so of course it splits into E1 tensor 1G plus E2 tensor 1G plus E1 prime tensor 1G plus E2 prime tensor 1G plus E3 tensor 1G. So it gives me like these 5 objects. So these are idempotent. But what happens is 2 things happen. So first thing is that this one and this one gives rise to the isomorphic object in the sense that this projective module is isomorphic to this projective module. So as a lambda G module. The same for these 2. So in fact, I can get rid of 1 if I want to understand this category, because I have like these 2 objects, they are isomorphic. And I want to understand the non-isomorphic object. And now I have this one, and this one is very special because it's a fixed point by the action of sigma. And since it's a fixed point by the action of sigma, it's not hard using this multiplication to see that, in fact, it splits into, okay, so here I'm working I mean, my field is C in all my talks, so I can divide by 2. In general, I should at least assume that I don't have characteristic 2 to be sure that it works. So I can write it like this, okay? I mean, this is also true for E1, that it split like this, but for E1, you can, this one is not an idempotent, but here you can check that this is an idempotent. And this also. So it means that this, in fact, gives rise to 2 objects, 2 indecomposable objects. So this one splits. And then the picture is, so now I want to understand the quiver of this algebra. So now I know the vertices. So they are given by idempotent, non-isomorphic idempotent. Well, isomorphism classes of idempotent, I should say. So now this proj KQ star sigma is, so here I have the E1 tensor 1G, which is the same as E1 prime tensor 1G. I have E2 tensor 1G, which is the same as E2 prime tensor 1G. Well, it's not the same idempotent, but it's an isomorphic object. And now I have 2 objects, which, oh no, it's not, yeah, which is E3 1 plus sigma over 2 and E3 1 minus sigma over 2. So here I get a DN quiver, and this is a bit the motivation of all this work. So for the gentle case, we obtain DAN quiver, and sort of the big family generated by NN quiver somehow, and here we get the DN quiver, and we could also get the DN tilde quiver, and this kind of construction. So I will just end by giving the definition of. So what we did with Pierre-Guy was to try to construct a good category in which we can work and make computation to understand these algebras, the derived category of these algebras. And then, so you start with S, a full system of graded arcs, but which is sigma invariant. We could also start with D, a full system of graded arcs, which is sigma invariant. No, here, sorry, a dissection. And the category we consider, so we copy this construction of skew group algebra, but at the level of A infinity category. So what we construct is, so we take A of S, there is an action of sigma on this category, which is as nice as you can imagine. So I could do this, and I get a new A infinity category. And this is the A infinity category I want to work with. So what do I do now? I take the twist of this. Oh, no. So, yeah, sorry. So now I have this category, and it's a nice A infinity category, but it has the same problem as before here. It has a problem that I have some idempotents that do not split. That split, but that you want to give you different objects. So what I need to do is to take the split completion of this category. So it's a split completion in the Seidel sense because it's for A infinity category. And then I take the twist, and then I take H0. And so this is a category. This would be this Fock of S over sigma. And the first thing is that, okay, it's good to have this definition, but with this definition, it's almost impossible to do computation because this Seidel split completion is just very abstract construction that already deal with twisted complexes. So now and then you end up with twisted of something, and twisted of twisted start to be a bit too much. So one first thing we proved is that in fact we can move this split completion and what we do is really, in fact, we can also move the star G. And here we can take the split completion of this, but this is just a category. And so this is a Karoubi split completion, and here you can do computation because this is something you have some control of. And then in this category, what happens is that if you have, so like in the picture here, so if you take a graded arc which is sigma invariant, then it gives rise, so this is in S, then it gives rise to two objects that I denote by plus minus using this plus minus that somehow correspond to a character of the group G, and I get these two objects in this Fukaya category of the orbifold. And what we could do is to understand the morphism between this new style object and to find some tilting object in this Fukaya category of the orbifold, and this gives some new derived equivalent algebra to this kind of algebra of type Dn or Dn tilde or this kind of algebra. So I will stop here. Thank you very much.